Hello, so this is the last worksheet for the logic unit. Um, it's a worksheet on Russell's paradox, but before we can tackle it, I want everybody to have the same background in set theory. So let's jump right into it. Um, Before we go further, this is a lot to take in. So if you have any questions, please post it on the Canvas website, on the discussion board, or the Discord channel where you can ask questions about paradox class, and I'll try to answer it as quickly as possible. All right, with that said, let's jump in. Okay, so let's talk about set theory. So what is a set? Set is collection of things. Things could be anything. The things in a set is referred to as its member or one of the elements. Okay, so for an example, here's how you might write down sets. So traditionally, when you name a set, you usually give it a capital letter. So maybe I'll name set A to be a collection of three numbers, 1, 2, and 3. So when you write a set, you want to encapsulate the set elements using curly braces. And between elements, you might use comma to separate them. So if I write curly braces, 1 comma 2 comma 3, end braces, that is a set of three elements, 1, 2, and 3. They don't have to be numbers. It could be colors, for example. So set B could be colors red, white, and blue. So, and you could collect anything. So notation of membership. So if you want to say one belongs to set A, you write it like this. So one is the element you're referring to, and this symbol, it looks like a lowercase c with a tongue sticking out. That says one belongs to this set A, or you might say one is in A, or one is a member of A, or one belongs to A. All of these mean the same thing, that set A contains this element 1. That's what that means. If you want to show that something does not belong to a set, you use the same symbol except slash through it. So if B was a set of red, white, and blue, green doesn't belong to it. So green is not a member of the set B. So that's how you write something like that. All right, some technical details. So set is described entirely by what it contains and what it doesn't contain. So if you write down two different sets or two sets like this, it looks like the set on the right has 4 elements, but notice one of the elements is repeated twice. So it turns out that if you list them twice, it doesn't matter. Like it already contains one, so listing it more than once does not affect the set at all. So the set on the right-hand side actually only contains 3 elements, 1, 2, and 3. And notice how listing it in different order doesn't matter either. So if you listed 2 before 1, that does not affect whether or not 1 or 2 belongs to the set. So what's written here and what's written here is exactly the same. So repeated membership doesn't matter, and order does not matter when you're listing the elements of the set. The only thing that matters is whether it belongs to it or not. Okay. You could also consider an empty set. So empty set is a thing that exists. So you could have a collection of nothing. So you might write it something like that. So open and close braces with no elements in between it. This is a set that kind of comes up often when you're talking about set theory. So it has a special notation. It kind of looks like the number 0, but it's really not. It's different from the number 0. It's a big circle with a diagonal slash through it. And this is a special notation we use for set that contains nothing. I kind of like to imagine it as an empty bowl. Okay, so listing elements to define a set is fine, but sometimes there's too much to list, and you can more succinctly describe a set by what's called the set builder notation. So what you could do is within a curly braces, you have this divider, so vertical bar going through the middle of the set. Sometimes this is replaced with a colon, just 2 dots. But what the set builder notation is saying is the left-hand side tells you what the actual element in the set is, and the right-hand side of the divider tells you the condition that element has to satisfy to be in the set. So if I write down the set of X such that you read this divider as the word such that. So X such that X is a color, right? So if X could be considered a color, it belongs to the set. Notice how there's infinitely many different colors. So you can't list all the colors. You have to do something like this to describe it. So this is another way to describe a set. Okay, so example, you could say X such that X is an even integer. Right? So these are all the even integers, and there are infinitely many of them. If the pattern is clear, you can kind of list it like this as well. So all the dots is saying, well, you just add 2 each time, right? So 0, 2, 4, 6, 8, 10, and so on. If the pattern itself is clear, you could just say ... to mean and so on. And you could do that in the negative direction as well. So both of these are equivalent way to describe the same set of even integers. Here's some like common notations that mathematicians use. So n, these are called blackboard fonts, where some part of that letter is kind of thick, right? So n is usually reserved for natural numbers. So these are counting numbers. Sometimes people do not include 0. Sometimes people include 0. So either way is okay, but for this class, let's say natural numbers include the number 0 and all the other positive integers after that. So 0, 1, 2, 3, all the numbers you use to count things is called natural numbers. Z is usually reserved for integers, so it includes the natural numbers as well as the negative integers as well. People use the letter Z because I think the German word for integer starts with a Z. Q is usually reserved for rational numbers or ratio of 2 different integers. So I could describe that using a subbuilder notation, right? So P divided by Q such that P and Q are integers, and you should also make sure that the denominator is not equal to 0 because you can't divide by 0. So this is how you could describe rational numbers. And I haven't written the description for real numbers. That's a little bit technical, but basically real numbers contains rational numbers, and it also contains irrational numbers where you can't describe it as two ratio. But you could think about it as all the limits you could make with these rational numbers. So the real numbers are all the numbers we usually think about, all the positive and negative numbers, including irrational numbers like square root of 2 belongs there. All right, so these are the letters that are kind of reserved for these special sets for numbers. Now I want to be able to compare different types of sets. So we say that a set A is a subset of another set B if everything in A is also contained in B. So B is at least as big as A. So then we say A is a subset of B, or the opposite way to say that is if B contains everything in A, you could rephrase that as B is a superset of A. They both mean the same thing, so you could use either language. And the notation we use look like this. So A is a subset of B. So this is the notation we use. It looks like less than or equal to symbol, but it's a little bit rounded. So that's the notation we use for set containment. So everything in A is also in B. If you want to make a distinction between A is a subset of B, but it's not equal to B, then you remove the horizontal line beneath the rounded part, and you might call this a proper subset of B. Okay. This is where everything in A belongs to B as well, but they're not equal to each other. So B has to contain at least one element that A does not contain for you to be a proper subset. Okay, so for example, if you have a set of 1, 2, and 3, that is contained in the natural numbers. So A is a subset of natural numbers. So you can kind of compare the two sets like that. So N contains A, basically. So I should talk about empty set a little bit. Empty set happens to be a subset of any set. Right? So if it doesn't contain anything, then everything in it is also contained in any other set, right? Because there's nothing. Everything contains at least nothing. So empty set is a subset of any other set. And empty set is different from a set containing an empty set. So you can make a set consisting of different sets. And if you have a set that has empty set in it, that is actually different from a set that has nothing in it. So remember the analogy I use for empty set. So empty set is like an empty bowl. And set containing an empty set is kind of like a bowl that contains an empty bowl. So there's 2 layers of bowls, right? So you could write down things like an empty set or set containing empty set or a set that has 2 elements, an empty set and a set containing empty set. So this is a big bowl that has 1 empty bowl and a bowl containing another bowl inside. So all of these things are different objects. So it is kind of confusing, but I wanted to make a point in saying that these are distinct things. So, okay. Set that has a set containing nothing is different from set containing nothing. All right. So a couple more things that you could do with sets. You could do, if you have a two sets, you can make a bigger set called a union, where this is a set that has all the elements from A and all the elements from B, or all the elements from both A and B together. So if you dump the two sets into a bigger bowl, that's what you call a union. An intersection is a set of the overlaps between the set A and B. So if you can find elements that are in both A and B at the same time, those elements are in the intersection of A and B. So these guys are smaller than both sets A and B. You could also talk about set difference. So if you write A backslash B, this means everything in the set A that is not contained in B. Okay. So let's kind of try to visualize these things. So if you have a set, you can kind of draw pictures of them. So usually, this is what's called Venn diagram. I'm a visual person, so these are very helpful tools for me. So what you do is you draw a rectangular box, and inside this box you draw a picture of sets. So here's a set A and here's set B, and the area inside of it is kind of representing elements that could be in there. Right? So if you have set A and B that does not share any elements, then you might draw it like that, where there's no overlap area. Here's a picture of a set where A is a subset of B. So area of A is entirely contained within this bigger set B. So that's a picture of what subsets look like. And I could kind of draw what union looks like. So union of A and B is this shaded area. So things that are in A, things that are in B, and things that are in both. So all of those combined area is the union. Intersection only counts the things that are in both. So this shaded area is inside of both the set A and B at the same time. So that's the area for intersection. And the set difference is all the elements in A that does not, it's not also in B. So all of the A elements outside of B. So this is the set difference right there. I hope all of these made sense. So what I want you to do at this point is tackle the last worksheet, worksheet 12 on Russell's paradox. You're now equipped to read the statement of Russell's paradox, and then kind of try to decide for yourself how you might resolve this paradox. It's a paradox about containment. Russell's paradox set R is all the sets that does not contain itself. Okay, and I want you to tackle this worksheet, and I don't want you to worry too much about whether you could resolve this paradox correctly or not. You have some experience looking at similar paradoxes. So I want you to do your best trying to see if you can try to resolve this paradox, but I'm not too worried about you getting it correct. So just give it your best shot. Okay, so this pretty much concludes all the worksheets. I have one more video ready for you today about the historical context of how this Russell's paradox shaped the course of development of mathematics. But after that, we're done. We will have a quiz based on this logic unit next week on Friday. So we'll have like a kind of recap video on Wednesday next week. Anyways, I will see you on the video for the historical context.